questions 11 through 20 on the 2018 Grade 10 AMC 10A. When 7 fair standard 6-sided dice are thrown, the probability that the sum of the numbers on the top faces is 10 can be written as n over 6 to the power of 7, where n is a positive integer. What is n? We have 7. 1, 2, 3, 4, 5, 6, 7. And each of these, when you flip it, when you roll it, you get 6 possible outcomes. The numbers 1, 2, 3, 4, 5, 6. So 6 outcomes here, 6 outcomes there, and so on, right? And then, of course, you have to multiply all those guys. And when you do, you get 6 to the power of 7. So, like any probability question, the probability is usually a fraction, and the denominator is the total number of cases, which we have just called or calculated as 6 to the power of 7. Now, the numerator is our specific condition that the numbers on the top of the faces equals 10. Okay, so how can they equal 10? Well, there's a few ways. You can have, I believe, all ones, 1, 1, 1, 1, 1, 1, and then 4. That's one way of doing it. Another way is if you had 5 ones, 1, 1, 1, 1, 1, and then you had a 2 and a 3. Not particularly in that order, but that's one possible way. Or if you had 4 ones, and then you have 2, 2, 2. I believe that would do it also. Yeah. So these are the scenarios. Now, 1, 2, and 3. There's only 3, right? And the answer choice is a lot bigger than 3. So obviously what that means is that each of these has different permutations. And that's what we have to calculate. Okay, so the first one, the 4 can go in any of those 7 slots. So from 7 slots, choose 1 for the 4. And that pretty much gives me how many different permutations there are. 7 choose 1, and 7 choose 1 is just 7. That takes care of that one. The next one, from the 7 slots, I've got to choose 2 of those for the 2 and the 3. And 7 choose 2 is 21. But each of those permutations can be flipped. So if I put 2, 3 like that, I can also put 3, 2. So therefore, I've got to multiply that 21 by 2, since each permutation can be flipped to give another one. So that gives me 42. And then for the next one, from the 7 slots, I've got to place these 3 2s. So choose 3 for those 2s. And 7 choose 3 is 35. So I add this 7 with this 42 and this 35. And that is what? 77 plus 7, 84. So 84 is what goes into the numerator. So that is my probability. And they've actually said that's n over 6 to the power of 7. So they've actually given us the denominator already. So I guess n is just 84. That's it. So number 11, the answer is E. How many ordered pairs of real numbers xy satisfy the following system of equations? X plus 3y is 3, and the absolute value of x minus the absolute value of y is equal to 1. All right. Well, as always, in these kinds of questions, we've got 4 different scenarios, right? The first one is when we have this scenario of x greater than 0 or y greater than 0. Now, from this guy right here, I can isolate pretty much that x is equal to 3 minus 3y. So what it really boils down to is really just 3 minus 3y is greater than or equal to 0, and y is greater than or equal to 0. The other one is 3 minus 3y is, say, less than 0, but y is greater than or equal to 0. The other one, you just flip those. So 3 minus 3y is greater than or equal to 0, but y is less than 0. And then finally, both of them are less than 0. 3 minus 3y is less than 0, and y is less than 0. And for each of these, we'll calculate this guy. So that means that the absolute value of x minus the absolute value of y is going to be either 1 or minus 1, because that's what would happen if you took the absolute value of the whole thing. As you can see, they took absolute value of the whole thing. So for the first one, looks like we have, since they're both greater than 0, it'll just be 3 minus 3y minus y is equal to 1. So that means 3 minus 4y is equal to 1. And therefore, it looks like y would be equal to 2 over 4. And therefore, y is equal to a half. In a very similar way, we do the same thing here, but this time for negative 1, 3 minus 4y would be negative 1. So 4y would be equal to 4, and then y would be equal to 1. So you can easily calculate x by putting it back into there, and when you do, for y equals a half, you get a value of 3 over 2. And then for y equals 1, you get a value of 0 for x. So those are our two pairs. So you do the same kind of thing for everything else. And since this is pretty straightforward, I'll just do it without walking you through it. So for the next one, this one right here, we're going to get 3y minus 3 minus y. Remember, this flips because it's less than 0 this time. And that equals 1. And this will give me y is equal to 2. And then if I do the 3y minus 3 minus y is equal to negative 1, that's going to give me y is equal to 1. So as before, substitute back into here to get the x values, and when you do, you get minus 3, 2, and 0, 1 again. Okay, well, let's do the other guys. This one would be 3y minus 3 minus y this time is equal to 1, and that's going to give me y is equal to 1. And then the other guy would be 3 minus 3y minus y is equal to negative 1, and that's going to give me y is equal to positive 2. And substituting back, you get the following values. You get 0, 1 again, and you get the minus 3, 2. And then finally, the last one, when you have them both being less than 0, we get 3y minus 3 minus y is equal to 1. That's going to give me y is equal to 1. And then the last one, it's just going to be 4y minus 3 is equal to negative 1. And that's going to give me y is equal to half. So this guy would be 0, 1 when you find out the x values, and 3 over 2, 1 half. So now we have to find the unique pairs. So we've got 1 here, 2, 3. This is a repeat, this is a repeat, this is a repeat, this is a repeat, this is a repeat. So only 3 unique pairs. So therefore, number 12, the answer is C. A paper triangle with sides of lengths 3, 4, 5 inches as shown is folded so that point A falls on point B. What is the length in inches of the crease? Well, if you're practicing, I encourage you to get out a piece of paper, make a little shape like this, and fold it and see what you get. And when you fold it, you will get a scenario where when you draw the crease, it would be something like this, right? It would be perpendicular to that side. And when you draw the line from that point to B, it will equal the distance from here to here. It basically creates 2 identical triangles where this is identical to that. So that is how the crease would form. Now we will label this. That, because this is isosceles, that's equal to that. That's going to create a scenario where this altitude chops the hypotenuse in half. So this would be 2.5 and this would be 2.5 since the whole distance is 5. Then we will start labeling things. I'll call this crease X. I will call this Y, and then therefore this distance will be 4 minus Y. And this distance is the same, so that's also 4 minus Y. Like that. Okay, so we've got a couple of Pythagorean relationships since this is a right triangle right here. So the first one, let's see here, we have, or what you can do is you can use similar triangles. I think that might be a little bit easier since this triangle is similar to that triangle since they have the same angles. So that means that if this is theta, this would be 90 minus theta right here. Squeeze that in there, 90 minus theta. And this angle will also be 90 minus theta. 90 minus theta. So based on that, or actually this side right here, which is 4 minus y, 4 minus y over this side, which is x, is equal to the hypotenuse here, which is 5, over this side right here, which would be 3. So cross multiplying, you get 5x is equal to 12 minus 3y, like that. And let's see what other similar triangle in the same kind of scenario, x over 2.5 would be the same as 3 over 4. So I think this is probably more beneficial. 4x is equal to 7.5, and therefore x is equal to 7.5 over 4. If you multiply top and bottom by 2, you get 15 over 8. There you go. Probably only needed to do just this. Makes it much more easier. So number 13, the answer is D. What is the greatest integer less than or equal to 3 to the power of 100 plus 2 to the power of 100 over 3 to the power of 96 plus 2 to the power of 96? Okay, well, there's several different approaches to this question. A quick way is to realize that 3 to the power of 100 is far greater than 2 to the power of 100. And similarly, 3 to the power of 96 is far greater than 2 to the power of 96. So this, in a very approximate way, could be just looked at as 3 to the power of 100 over 3 to the power of 96. And then that just simplifies to 3 to the power of 4. And 3 to the power of 4 is 81. And they're saying, what is the greatest integer less than or equal to that? Well, it's not going to be exactly 81. It would be slightly bigger than that because you've got a little bit more on the numerator and denominator. So less than that would be, of course, 80. The biggest integer less than this number. Now, the numerator is obviously being approximated, and so is the denominator. And if you're not convinced of that, no problem. We'll try a different method that perhaps will be more convincing. So let's take this and let's bring it over here. And what I'm going to do is make some substitutions. So let 3 to the power of 96 be A, and let 2 to the power of 96 be B. So since 3 to the power of 100 is equal to 3 to the power of 96 times 3 to the power of 4, it becomes A times 3 to the power of 4. And similarly, since 2 to the power of 100 is 2 to the power of 4 times 2 to the power of 96, it becomes 2 to the power of 4 times B. So this expression right here is really 3 to the power of 100, which is 3 to the power of 4 times A, plus 2 to the power of 4 times B, all over A plus B, like that. So 3 to the power of 4 is 81, 81A, and this is 16B over A plus B. All right, so now what I'm going to do is break this up I'm going to write, this one will stay the same, but then I'm going to write a 81b minus 65b. That basically equals 16. But when I break it up like that, it helps me, as I hope you will see. Now we can break this up, 81a plus b all over a plus b. And then the other would be just 65b over a plus b. Like that. Well, here the a plus b's cancel and we just get 81. And then here we've got some unknown value, 65b over a plus b. Okay. Now, at this point, I want you to think about this a little bit. This number here, we have no idea what it is, right? Well, we kind of do, but we don't have a calculator to our use, so we have to approximate. One thing is for sure, is that a plus b is this denominator, which is 3 to the power 96 plus 2 to the power 96. So that's a very, very big number. And the top is 65 times b, and b is 2 to the power of 96. So this must be less than 1. This has to be less than 1 because the denominator is so much bigger. So that means if I approximate this whole thing, it's 81 minus some very small fraction. So it's 80 point something. I don't know what, but 80 point something. So there you go. So they're asking, what is the greatest integer less than or equal to that? Well, the greatest integer less than or equal to 80 point something would be 80. So hopefully that's a little bit more convincing of a solution. So number 14, the answer is A. Two circles of radius 5 are externally tangent to each other and internally tangent to a circle of radius 13 at points A and B, as shown in the diagram. The distance AB can be written in the form m over n, where m and n are relatively prime positive integers. What is m plus n? Well, as always, let's draw a diagram. Let's put the center of the circle, which is approximately here, and connect it to A, and connect that same to B. And then let's join A to B, and I think one more line that is a perpendicular where it creates a right angle like that. I think that should be sufficient. Now let's label this now. One more line, I think, between the two centers of the smaller circles. Okay, there we go. I think now we're ready. So the radius is 5, so this is 5, this is 5, this is 5, and this is 5. And then the big radius is 13, so that means this is 3 and 3. So if A to B is, let's say, call it D, I guess, D for distance, then from here to here would be D over 2. Okay, so I see a similar triangle relationship. This triangle is similar to the bigger triangle. So that means D over 2 over the hypotenuse of the big one, which would be 13, is equivalent to this distance, which is just the radius. Yeah, that's just the radius, so that's going to be 5 over the distance from there to there, which is 8. All right, that's it. Cross multiply, 13 times 5 is 65. D over 2 times 8 would be 4D, and therefore the distance is 65 over 4, where D represented the distance from A to B. And that is indeed in the form m over n. M and n are relatively prime to each other. That basically means that it's in lowest terms. And now they just want you to find m plus n, and that's going to be 65 plus 4, which is 69. Number 15, the answer is D. Right triangle ABC has lengths AB is 20, BC is 21, including AB and BC. How many line segments with integer length can be drawn from vertex B to a point on the hypotenuse AC? Well, let's draw a triangle, and 21 and 20, right? So very close to each other. Okay, and let's label this now. So we've got A, B, and C. This is 20, this is 21. Now, how do we approach this question? The first thing I want to find is AC, and I think that will help me get sort of a baseline as to what kind of numbers I'm dealing with. AC squared, since it's a right triangle, would be 20 squared plus 21 squared. And that's me. AC squared would be what, 841? I think so, 841. And that means AC is 29. Okay, great. So now what I'm going to do is draw a perpendicular from B to the other side. And that perpendicular will help me figure out what kind of shortest possible value I can get for a line drawn from B to the other side. And how I do that is using the area. So one way of figuring out the area is 1/2 base times height, where 21 is the base and 20 is the height. Another way to figuring out the area is 1/2 base times height, where 29 is the base, and that line I just drew, which I'll call H, is the height. This gives me 21 times 20 over 29 is equal to H, and that means H is approximately 14.4 or something like that, approximately. So that means the shortest distance from B to H is 14.4 approximately. So the shortest integer would be 15, or smallest integer, I guess. And then we can keep going like that, 17, 18, 19, 20, all the way up into 21, because they're saying that including A, B, and BC. So since AB is 20 and BC is 21, that's pretty much the biggest. Now, how many did I get? 1, 2, 3, 4, 5, 6, 7. But 7 is not one of the answer choices. So what happened? Well, the reason is because some of these you can get twice. 15, for example, can be drawn like that. It can also be drawn like that. So there's two ways of getting that. 16 in the same way could probably be something like that and something like this. So as you can see, each of these can be drawn in two ways. 20. Well, 20 is obviously drawn like that, but you could also get one like that. But 21 can only be drawn in one way, and that is from B to C. So I got 2, 2, 2, 2, 2, 2, 1, and when you add those up, it is going to be 6 times 2 plus 1, 13. So number 16, the answer is D. Let S be a set of 6 integers taken from 1, 2, all the way to 12, with the property that if A and B are elements of S with A less than B, then B is not a multiple of A. What is the least possible value of an element of S? Okay, well, let's start with the least possible of the answer choices. So, I've got to make a set with 6 numbers. And the criteria is that no element can be a multiple of another. So if I start with 2, which is the smallest of the answer choices, what can I choose? Can I choose 3? Sure. Can I choose 4? No, because 4 is a multiple of 2, and that's not allowed. Can I choose 5? Yes. 6? No, because 6 is a multiple of 2 and a multiple of 3, so that's not good. 7 is fine. 8? Can't choose 8 because that's a multiple of 2. 9? Can't choose 9, that's a multiple of 3. 10? Can't choose that because that's a multiple of 5. 11, that's good. The only other number left is 12, but 12 is a multiple of 2. It's a multiple of 3. So 2 obviously doesn't work, so can't have that. Okay, let's try again, this time with 3 as my smallest. 4, no problem. 5, good. 6 can't go there because 6 is a multiple of 3. 7, I can do that. 8 can't go there because 8 is a multiple of 4. 9, can't put a 9 because that's a multiple of 3. 10, can't put 10, that's a multiple of 5. 11, I can. Now the only number left is 12. If I put 12, that's invalid because it's a multiple of 3. It's also a multiple of 4. Okay, 3 didn't work. Let's try 4. Put 4 as my smallest. 5, no, that's good. 6 is good. 7 is good. 8, can't put 8 because that's a multiple of 4. 9, can I put 9? Yes, I can. 10 is a multiple of 5, can't put that, but I can put 11. And there you go. I just created a set that satisfies the conditions in the question stem. And the smallest value in this set was 4. So therefore the answer is C. How many non-negative integers can be written in the form here, where ai is an element of -1, 0, or 1 for I between 0 and 7 respectively? All right, well, the first thing I want to do is write out these powers of 3. So it's 2187 plus 729 A6 plus 243 A5 plus 81 A4 plus 27 A3 plus 9 A2 plus 3 A1, and then finally just the 1 A0. Now, they want a non-negative. Interesting word, non-negative. It basically means 0 or positive. So the first thing, of course, is how do I get this to be 0? Well, 0 is if they're all zeros. So all of these A's were chosen to be 0. And there's only one way of doing that. If they're all zeros like that, then that pretty much takes care of this part, the 0 part. Okay, so there's only one way of doing that, so we'll put that out there. Now, as you can see, we have a lot more to go. And now we want to figure out positive. How do we get a positive? Let's concentrate on this guy right here. If that is positive, then this whole expression will be positive regardless of what anything else is, because even if all of these are negative, every single one is negative, it would still be less than 2187. And you can do the math. You can add up 729, 243, blah, 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 and you would get a number less than 2187. So the 2187 overrides everything. So if this is positive, any combination for any other term is valid in order to get the whole expression to be positive. So let's figure out how many combinations are there. For this guy, for A, we have 3 choices, right? Either -1, 0, or 3. So we have 3 choices. Similarly, for A5, we have 3 choices. 3 choices for A4, A3, A2, A1, and A0. Then you multiply them all together to get the total number. And that looks like 1, 2, 3, 4, 5, 6, 7, 3 to the power of 7. And 3 to the power of 7 will be the number of different ways of making the term, with this term being positive. And the only way it's positive is if you choose 1 for A7. So basically, A7 had to be equal to 1. Okay, so hopefully that made sense. Now, let's say that A7 is 0. Okay? Now, so that one's gone. Now I have to try to make the rest of these guys positive when you add them all together. It's the same sort of story. That will only happen if A6 is positive. So A6 has to be positive. So A6 has to equal 1. If A6 equals 1, any combination of the remaining terms will result in the whole thing being positive. Because 2, 4, 3, 81, 27, 9, 3, and 1, when you add them up, they are less than 729. So even if they were all negative, the 729 would still override it. So now we got to figure out what are the combinations, how many permutations. Well, for A5, we've got 3, A4, 3, 3, 3, and 3, and 3, right? Each of them can be either -1, 0, or positive 1. So this is what? 3 times 3 times 3 times 3 times 3 times 3. That is 3 to the power of 6. All right, so I hope you get the point. And if you keep doing that, you'll notice that you will get a pattern here. If you get this to 0 and this to 0, and this is going to be positive by making A5 equal to 1, it's the same story. 3, 3, 3, 3, 3, which is 3 to the power of 5. And therefore, you will get a pattern all the way down to 3 to the power of 0. and I'll just fill them all out. And there you go. That's about as complete as I can possibly make it. And then as you can see, it's 3 to the 7 plus 3 to the 6 plus 3 to the 5, 3 to the 4, 3 to the 2, 3 to the 1, 3 to the 0. And when you add up all those guys, 3 to the 7 plus 3 to the 6th plus 3 to the 5 plus 3 to the 4 plus 3 to the 3 plus 3 to the 2 plus 3 to the 1 plus 3 to the 0. When you do that math, you get 3280. And remember, at the very beginning, we had a scenario when there were all zeros, and that had given me one scenario, and I've got to add that to the 3280. And therefore, the grand total is 3281. And 3281 is choice D for number 18. A number M is randomly selected from the set 11, 13, 15, 17, 19, and a number N is randomly selected from 1999 to 2018. What is the probability that m to the power of n has a units digit of 1? Well, let's start with 11. 11 to the power of 1, 11 to the power of 2, 11 to the power of 3, 11 to the power of 4. Let's get an idea of what the units digits are. Well, that's 11, that's 121. That's 1331, and that's 14641. Units digit is always 1 in this case. So that means the probability there is just 1. Probability, P equals probability. So there we go. That took care of the 11. Now let's talk about 13, the next one in the list. So 13 to the power of 1, 13 to the power of 2, 13 to the power of 3, to 13 to the power of 4. That's 13, that's 169, that is 2197, and this is 28561. And this is a repeating pattern, 3971, like that. So the probability that the units digit is 1 here is 1 out of 4 because it repeats 3971, the units digit. Okay, but here's the thing. That's generally speaking. But you got to be careful here because they've given us a certain set. We have to figure out in that set only, not generally speaking. Okay, so how do we do that? In this case, we didn't really matter. It's always 1, so we didn't really need to care about the set here. But in this one with the 13s, we need to care. Every time the exponent is a multiple of 4, that's when the units digit will be 1. So the exponent has to be a multiple of 4, so the number here has to be a multiple of 4. How many multiples of 4 are there? 2000, 2004, 2008, 2012, and 2016. So I guess the Olympic years. And how many are there in total? It looks like 20. There's 20 numbers here. So 5 out of 20 is the actual probability. Well, 5 out of 20 is 1/4. So we got a little lucky there. But I really wanted to emphasize that you actually have to concentrate on that set and not just figure it out and then move ahead. So it is 1/4. I'll just write 5 over 20 just to be complete. Okay, now let's move over to 15. 15 to the power of 1, 15 to the power of 2, 15 to the power of 3, and so on. That's just 15. 15 squared is 225. 15 to the power of 3 is 3375. 15 to the power of 4 is 50625, and so on. So the units digit here is always 5. So it's never 1. So the probability of it being 1 is 0. Okay, interesting. Well, let's go to 17 now. 17-1, 17-2, 17-3, 17-4. So 17 squared is 289. 17 to the power of 3 is 4913. 17 to the power of 4 is 83521. And this just keeps repeating, 7931, like that. So as before, it looks like every time the exponent is a multiple of 4, the units digit will be 1. And very similar to the 13s, this is going to be 5 over 20, which is 1 over 4. Okay, we're down to 19, the last one. 19 to the power of 1, 19 to the power of 2, 19 to the power of 3, 19 to the power of 4. Gives us an idea what the units digit are. This is 19. This is 361. This is 6859. And then this is 13321. Okay, so this actually repeats 9191 like that. Okay, that's interesting. So that means that every time the exponent is even, the units digit will be 1. So how many of these 20 numbers are even? 10 of them. So the probability is 10 over 20, which is just a half. Okay, interesting. All right, so now we got to combine them. So the total probability. Each of these numbers has an equal chance of being selected, 1 over 5. So 1 over 5 is the chance of selecting the 11. When you do, the probability of getting a units digit of 1 is 1. Then the 13 has a 1 over 5 chance of being selected. Probability that the units digit is 1 is a quarter. 15, 1 over 5 times the probability, which in that case was 0. 17, 1 over 5, the probability there was 1/4, and finally 1 over 5, and the probability there was 1/2. When you do this math, you get 1, 5, 120, 0, that cancels 120 and 1 over 10. So that is going to be 24 plus 1 plus 1 plus 2, and that is 8 over 20, and in lowest terms 2 over 5. And there we go, 2 over 5. Number 19, the answer is E. A scanning code consists of a 7x7 grid of squares with some of its square colored black and the rest colored white. There must be at least one square of each color in this grid of 49 squares. The scanning code is called symmetric if it does not change when the entire square is rotated by a multiple of 90 degrees counterclockwise around its center, nor when it is reflected across a line joining opposite corners or a line joining midpoints of opposite sides. What is the total number of possible symmetric scanning codes? Okay, I'm going to read this. The diagram below shows the orbits of each square under rotations and reflections. Because the scanning code must look the same under these transformations, all squares in the same orbit must get the same color. But one is free to choose the color for each orbit, except for the choice of all black and all white. Because there are 10 orbits, there are 2 to the power of 10 minus 2, which equals 1022 symmetric scanning codes. All right, so please allow me to explain. What they've done is they've assigned each square a letter. So for example, this is A. And then they've said, when you rotate it or when you reflect it, where else will it be? Well, if it starts off A and you rotate it, it will go here. If you reflect it, it could go here. If you rotate it again, it would go here. So those ones will always be A because of rotations and reflections. In a very similar way, let's say this is D. If you rotated it, it would come here. If you reflected it, it would go here. If you rotated it again, it would go here, and so on, right? So all of those squares would be represented by the same letter D, and so on. They've done that for every single square. It's quite a bit of work here, but it's a very good way of understanding the question. And then what they've said is that for each of those letters, what are the possible choices? Or for each letter, it can be either black or white. So there's only 2 choices for each letter. How many letters are there? Well, the letters go up to J. So that means there's 10 letters. A, B, C, D, E, F, G, H, I, and J. So each of these has 2 possible colors. It could be either black or white. So the total number of possible, combinations or, total possible ways of doing this is 2 times 2 and so on, which is essentially 2 to the power of 10, which is 1024. Now what they said is that there's two possible outcomes that you have to subtract. That one is where everything was chosen to be white, and the other is when everything was chosen to be black, because these two are not allowed, because the question actually tells you that there must be at least one square of each color in this grid of 49 squares. So you can't have all 49 white or all 49 black. So these two, are not allowed. So from this 1024, you have to subtract 2, and when you do, you get 1022. So that is how this question is done. Number 20, the answer is B.